The last part of Lecture 11 deals with the relationship of K, change in enthalpy, and temperature. So our two main formulas to give us delta G at standard state are minus RT natural log of K and delta H naught minus T delta S naught. I'm going to take minus 1 divided by T times these two relationships. So on the left side, I'll get R natural log of K, and on the right side, I'll get delta S naught minus delta H naught divided by T. Suppose that I get the equilibrium constant at two different temperatures. So one of my equations will apply to temperature 2 and equilibrium constant 2. The other of my equations will refer to equilibrium constant 1 at temperature 1. And I subtract these two equations. The net equation I'm going to get will be R times natural log of K2 minus R times natural log of K1. The delta S terms will cancel out, and I'll get delta H naught divided by T1 minus delta H naught divided by T2. I can simplify this further by bringing the delta H naught term out of the temperature term, so those are isolated. And I could multiply this whole set of equations by 1 divided by R. So I will get natural log of K2 is equal to natural log of K1 plus delta H naught over R multiplied by the term 1 divided by T1 minus 1 divided by T2. So what you see here is, if you know the change in enthalpy at standard state for a reaction and the equilibrium constant at one temperature, you can solve for the equilibrium constant at another temperature. Or you can get the equilibrium constant at two different temperatures and solve for the change in enthalpy. So this is definitely a formula that would be given to one on a formula sheet because it's pretty complex. But this is another way that chemists go about getting these changes in enthalpy. So here is a question that uses that relationship. We are given that octane has a vapor pressure of 13.95 torr at 25 degrees Celsius and a vapor pressure of 144.78 torr at 75 degrees Celsius. And we're asked to calculate the change in enthalpy of vaporization in kilojoules per mole. So you know our equation deals with equilibrium constants, and you may be saying, I don't see any equilibrium constants. Vapor pressure is an equilibrium constant. And we are given vapor pressure at two different temperatures. So the equation we're looking at is octane in the liquid phase in equilibrium with octane in the gaseous phase. So that means our equilibrium constant is going to be the pressure of the gas divided by 1. Now we still need to do a little bit of work because when you're working with equilibrium constants, standard state is units of atmospheres. We are given our vapor pressure in torr. So we're going to need to use that factor to correct for this. So for my equilibrium constant at 25 degrees Celsius, I'm going to take 13.95 torr and divide it by 760. So my equilibrium constant at 25 Celsius is 0.018355 atmospheres. Your first job in solving this problem is to get the equilibrium constant at 75 degrees Celsius. Now it's time to use our formula. So I'm going to mentally assign my equilibrium constant at 25 degrees Celsius as K1 and my equilibrium constant at 75 degrees Celsius as K2, which means T1, which is at 25 degrees Celsius, is going to be equal to 298.15 Kelvin, and T2 at 75 degrees Celsius is going to be equal to 348.15 Kelvin. As far as the R goes, we are trying to get energy units for our enthalpy change, so we should use the 8.314. So now let's substitute. So we'll have natural log of K2, which you should solve for, equals natural log of 0.018355 plus delta H naught divided by R. We're going to use 0.008314 kilojoules per Kelvin mole multiplied by the quantity 1 divided by 298.15 Kelvin minus 1 divided by 348.15 Kelvin. So to help you with your math a little more, I get minus 1.648 is equal to minus 3.9979 plus delta H naught, which I'm trying to solve for, divided by 0.008314 times 4.8169 times 10 to the minus 4. You notice that our units are such that on the right side we'll be left with moles per kilojoule, which when we solve for delta H naught will give us a value of kilojoules per mole. So that's how you do part A. Once we have delta H naught, we can use these relationships to get delta S naught. So I remind you from the previous problem that the equilibrium constant at 25 degrees Celsius is 0.018355 atmospheres. We can figure out delta G using minus RT natural log of K, and then with our knowledge of delta H naught, use the second formula to get delta S naught. So substituting all those values in, we have delta G at 25 equal minus 0.008314 kilojoule per Kelvin mole times 298.15 Kelvin times the natural log of our equilibrium constant at 25. This will give us 9.90995 kilojoules per mole. So now we can use that value and the delta H naught value that we calculated in part A to solve for delta S naught. One quick note on units. We are being asked for delta S naught in joules per Kelvin mole. When you do this calculation, it will yield your answer in kilojoules per Kelvin mole. So don't forget to multiply your answer by 1000. Our last question asks us to get the normal boiling point of octane in degrees Celsius. Remember that at the boiling point, our vapor pressure will be 1 atmosphere. So K will be 1 and delta G naught will be 0. So our boiling point temperature will be delta H naught divided by delta S naught. Now, of course, in order to do this, make sure you use your delta S naught in kilojoules per Kelvin mole. And you know this will spit out your answer in units of Kelvin. Remember that degrees Kelvin is degrees Celsius plus 273.15. So we're going to need to subtract that value in order to get our answer in degrees Celsius. And one last problem using this formula. Now we would like to know the vapor pressure at 0 degrees Celsius. So first we can think about this problem conceptually. At 75 degrees Celsius, the vapor pressure is 144.78 torr. The vapor pressure goes down when the temperature goes down to 13.95 when we are at 25 degrees Celsius. So at 0 degrees Celsius, we certainly expect our value to be lower than 13.95. So here we're going to solve for K2 at 0 degrees Celsius, which is 273.15 Kelvin, and I will assign K1 as our previously determined value of 0.018355 in units of atmospheres at 25 degrees Celsius, which is 298.15 Kelvin. So that means natural log of K2 is equal to natural log of 0.018355 plus delta H, which, if you're still with me, now you know the value, 40.386 kilojoules per mole, divided by 0.008134 kilojoule per Kelvin mole, times 1 divided by 298.15 minus 1 divided by 273.15. So eventually you should get to minus 3.99785 minus 1.49116. And I trust you know to raise both sides to the power of e to get rid of the natural log. This will give you your K2 in units of atmospheres. And please remember to multiply by 760 torr per 1 atmosphere in order to get your answer. This equation is not the only way to answer question D. You could, now that you know the values of delta H naught and delta S naught, calculate the value of delta G naught at 0 degrees Celsius, and then calculate your equilibrium constant as E raised to the minus delta G divided by RT, and then multiply by 760 to convert it to torr. So, to summarize Chapter 4, entropy is the disorder of a system, and we know that gases have much more entropy than liquids, which have more entropy than solids. We looked at some ways that energy could be distributed and found that systems with energy levels that are close together have more entropy than when the levels are further apart. And the quantitative description of entropy is change in entropy equals heat divided by temperature. We can use our tables to find the entropy change of a reaction as the sum of the coefficients times the entropies of the products minus the sum of the coefficients of the reactants times the entropy of the reactants. Thinking about the entropy of the universe got us to the Gibbs free energy equation, which is shown below, which incorporates both enthalpy and entropy into a calculation of the total free energy of the system. And if we work at constant pressure and temperature, when we have a negative delta G, the forward reaction is spontaneous. When we have a positive delta G, the reverse reaction is spontaneous. And if delta G is equal to 0, we are at equilibrium. If we need to correct for non-equilibrium conditions, we can get the free energy is equal to the free energy at standard state plus a little adjustment factor, RT natural log of Q, which is the reaction quotient. If we want to get free energy change at temperatures other than 298, we take our delta H naught at 298, our delta S naught at 298, and multiply it by the temperature in Kelvin. It's easy to go between delta G naught and K using either of these formulas. One way to compare non-equilibrium with equilibrium conditions is to look at the free energy change, which is set equal to RT natural log of Q over K. So we are comparing the reaction quotient to the equilibrium constant. And at the boiling point, or the flip temperature of a reaction, delta G naught is equal to 0. So our temperature in units of Kelvin will be delta H naught divided by delta S naught.